here are a couple of related rates problems. And really rates problems are all about kind of the setup. So this problem says the radius of a circle increases at 4 inches per second. How fast is the area of the circle increasing when the radius is 20 inches? So the idea here is that I've got some circle, right? And its radius is increasing. So maybe, after 1 second, the radius is 4 inches. After 2 seconds, the radius is 8 inches. After 3 seconds, the radius is 12 inches, right? I can't really draw it super big, right? But the area isn't increasing linearly, right? So the radius is always just increasing by 4. But the area, right here, the area would be, pi r squared is 16 pi inches squared. Here would be 64 pi inches squared, and that increased, by 48 pi. Here would be 144 pi, which is going to be like 80 pi or more. So, right, we're increasing more and more every time. So what we need to do is we need to write some relations, it's called related rates for a reason. So here's what I know. Well, first I need to ask, what's changing? I know there's an equation you all want to write down. Before you write down that equation, you want to ask yourself, what's changing? Well, the radius is changing. And we know how the radius is changing. We know the radius is changing. So I'm going to write dr dt. That's the rate the radius is changing at with respect to time. It's changing at 4 inches per second, right? Length per time, radius per time, length per time. And we also want to know how the area is increasing. I don't know that yet, but I want to find it. I'm going to write down how area is increasing as dA dt, the rate of change of area with respect to time. And we don't know that. Now that we've identified the things that are changing, area and radius, and time is always changing, but we kind of don't think about that one as much. We want to find an equation relating those two variables. It's usually going to be some geometric or Pythagorean kind of equation. Here it's just the area of the circle. Right? We know that the area of a circle is pi times the radius squared. Then we want to take the derivative, but we have to be careful. We're not differentiating with respect to r, we're differentiating with respect to time. So we're kind of thinking of r as really some stuff. Right? R is a function of time, if you like. And so when we differentiate that, we're going to have to use the chain rule. Right, so the derivative a of t is a prime of t. Pi times some stuff, the derivative is pi times, the derivative is r of t squared is 2 times r of t to the first times the derivative of the stuff. And usually we don't write it like this. We usually say, oh, well, a prime of t is dA dt. And the derivative of pi times r squared is pi times 2r times dr dt. So whenever you differentiate some function to a power or whatever, we know that that function is actually a function of time, so we have to use the chain rule multiplied by its derivative. Then we're going to plug in what we know. So if I plug in, well, let's see, I know that I'm trying to find dA dt. I've got pi times 2, or 2 pi. I know that the radius is 20 inches because we're asking how fast is the area increasing when the radius is 20 inches. And we know that dr dt is 4 inches per second. Now, I don't usually write the units, but if I do, I can see it's going to work out. That's 20 inches, that's 4 inches per second. When I multiply them together, I get inches times inches, or inches squared per second. So this is going to be 2 pi times 20 times 4, math. 2 times 20 is 40, 40 times 4 is 160. So you get 160 pi inches squared per second. And it probably is important to write the units when you're doing these sort of problems. Right, here's another one. 2 cars leave Davis, one driving east at 40 miles per hour and one driving south at 30 miles per hour. After 2 hours, how fast is the distance between the cars increasing? So I like to draw a picture. So car 1 is going east. I'm going to call the length it's traveling x, and it's going at 40 miles per hour. Drawing the pictures is important. We have another car going south, and let's call this distance y, and it's going south at 30 miles per hour. So here's what I know. So the things that are changing, and so it's really important when you're trying to figure out what's changing to label your picture, right? If I just said this was some distance, I would know. But I know that this length is x, x is increasing, right, as time goes on. So I know that dx dt is 40 miles per hour. I'm just going to say 40. I know that dy dt, y is also increasing at 30 miles per hour. And I want to know how fast the distance between them, which I'm going to call s, is changing. And so just like before, we're going to write an equation relating the non-time variables, x, y, and s. Here it's pretty clear, I think, that it's the Pythagorean theorem, right? You've got this squared plus this squared equals this squared. That's step 2. And then step 3 is to differentiate with respect to time, right? So the derivative of x squared isn't going to be just 2x, it's going to be 2x times dx dt. So you get 2x times dx dt, right? Just like on the previous one, the derivative of r squared was 2 times r prime, or 2r times dr dt. The derivative of x squared is 2x times dx dt, or 2 times x prime. Same thing for y squared. Y also depends on time, right? This length depends on what time it is. So we're going to get the derivative is 2 times y times dy dt. And lastly, this length also depends on the time. So we're going to get 2 times s times ds dt. And then we're going to plug in what we know and solve for what we don't. We hope to know everything except for this and solve for that. So let's see. After 2 hours, I know that x is going to be 80 miles. So I get 2 times, well actually, so here's the thing you can do which makes it a little easier. You can divide everything by 2, right? We've got a 2 there, and there, so let's make life a little easier. So after 2 hours, x is going to be 80. I should say right after 2 hours. I know that x is 80 miles. I know that y is 60 miles. Oh, sorry. This one's 40. This one's 30. And y is 60 miles. And I know that s is, well, if I use the Pythagorean theorem, s squared is 80 squared plus 60 squared. Now, 3, 4, 5 right triangle is a nice thing. This is actually just a multiple of that. Right? This is a 3, 4, 5. It's a 30, 40, 50. It's a 60, 80, 100. You can also do the math, right? 80 squared is 6,400. 60 squared is 3,600. Those add up to 10,000, which has a square root of 100. So s is equal to 100 miles. So now I can plug in for everything, right? X is 80. Dx dt is 40. Y is 30. Dy dt, sorry, y was 60, not 30, right? Y is 60. Dy dt is 30. And s we found to be 100. And we can solve for ds dt. Now notably, I didn't write the units again, but let me point out what we've got. And I've got 80 miles times 40 miles per hour. So I have miles squared per hour. Same thing here, miles squared per hour. And here I have 100 miles. And so when I divide the 100 miles over, I'll have miles squared per hour divided by miles, which will just be miles per hour, which makes sense for what ds dt should be. Usually the units should just work out, so you can just ignore them until the end. So this is going to be 3,200 plus 1,800 divided by 100. So I get 5,000 divided by 100, which is 50. So at that particular moment in time, ds dt is 50 miles per hour. The rate of change of the distance between the two cars is 50 miles per hour. So there you go. Pretty neat.